Le Chatelier principle describes how a system at equilibrium responds to external changes to minimize the impact of those changes. To grasp this, you must first master 1. Dynamic equilibrium, the state where the rate of the forward reaction equals the rate of the reverse reaction. 2. Equilibrium constant, K, the numerical expression of the ratio of products to reactants at a specific temperature. 3. Reaction quotient, Q, how the current state of a system compares to its equilibrium position. This connects to chemistry by allowing us to manipulate industrial processes to maximize yield. If a system is in balance, what effect do you think adding more reactant has on the frequency of successful collisions between reactant particles? Welcome to the Mastery Path. Select a module to begin your journey. Module environment loaded. We will review the theory and complete the assessments. Matter Basics. To start today's lesson, let's step back into the laboratory. Select the Matter Basics Lab tab. Observe the 4 beakers on your screen. They contain a gold coin, pure water, salt water, and a dry mix of sand and iron filings. As you examine them, think, how do these samples differ at the microscopic level? How can we use their physical and chemical properties to classify, separate, and transform them? In this lesson, we will systematically classify matter, physically separate mixtures, and mathematically track the conservation of mass during chemical changes. Section 1. Recap: Chemical domains and the scientific method. In our first lesson, we defined chemistry as the study of matter, anything possessing mass and occupying volume. We learned to investigate nature across 3 chemical domains: the macroscopic, everyday observations like boiling liquid water; the microscopic, the behavior of individual H2O molecules too small to see; and the symbolic, the shorthand formulas and phase labels like H2O liquid and H2O gas that we write. To explore these domains, chemists use the scientific method, a systematic path of discovery where we make observations, formulate testable hypotheses, conduct controlled experiments, and refine laws and theories to describe and explain the natural world. Computational molecular modeling uses mathematical algorithms to simulate chemical systems. It allows us to predict the properties and behaviors of matter before performing experiments in the physical laboratory. To approach this, you must first master 1. Schrödinger equation, the foundational wave equation describing the energy and behavior of quantum systems. 2. Born-Oppenheimer approximation, a method that separates nuclear and electronic motion to simplify calculations. 3. Basis sets, mathematical functions used to represent atomic orbitals within a simulation. This field connects to all of chemistry by providing a predictive, virtual framework. If we want to simulate how atoms interact, what do you think is the primary physical force we must calculate between all charged particles in the molecule? The ideal gas law, PV equals nRT, provides a mathematical relationship between pressure, volume, temperature, and the amount of gas. To master this, you must first understand 1. Kinetic molecular theory, the model describing gas particles as points in constant, random motion. 2. Pressure and volume, how collisions of these particles against container walls manifest as macroscopic pressure. 3. Temperature as kinetic energy, the direct relationship between thermal energy and particle velocity. This connects to the rest of chemistry by allowing us to account for mass in reactions involving gases, especially when dealing with the law of conservation of mass in open systems. If you double the volume of a container holding a gas, how does that impact the frequency of collisions with the walls?